Hi there, welcome to the video on differentiating log functions. We have already reviewed details about the definition of logarithms as well as the laws used to manipulate them and the ways to graph the log functions. So it's now time to get into the applications of calculus. So we will start our learning by reviewing the graph of y equals log x again. Again, we note that the intercept on the x-axis is at x equals 1. The y-axis is an asymptote for the curve, and the curve always has a positive gradient, so it is always increasing in value. Now when the y value of x is very small, very close to 0 in other words, the log curve is very steep, and so its gradient must be a very large positive number. So if we now regard the vertical axis as either the y-axis or as a derivative axis, then we can add an entry at the very top to show that close to 0, the curve has a very large gradient. Next, we look at the right-hand side of the curve. Here the curve is becoming more horizontal, so therefore its gradient must be becoming smaller. We therefore add an entry at the right to show a very small gradient. The two small blue marks which I've added to the graphs can now be joined with a gentle curve to reflect the gentle curve and the gentle change in the gradient of the log curve. Our new blue curve, which has been added, looks like a hyperbola, and it is. So from this brief exploration, we can infer that if y is equal to log x to the base e, or if we wish to write it ln x, then the gradient function dy dx is the equation of a hyperbola, which is 1 over x. So you must remember that result, and you will, because you will be using it so much. So let's have a look at some examples on how to take derivatives of log function using that result. We combine the basic result for the log differentiation, which we just developed, with the last step in the chain rule. So we say to ourselves, and it's important to talk to yourself when you're doing your maths because it helps your concentration on the task and you don't try to do funny things. So I want you to say from this point on that the log function goes to 1 over the function times the derivative. So if we have y is equal to log 2x plus 1 to the base e, then dy dx is going to be 1 over the function, which is 1 over 2x plus 1, times the derivative of 2x plus 1, which is 2. So we can put those two terms together and we have 2 over 2x plus 1. If we have y is equal to log 3 minus 5x to the base e, then dy dx is going to be equal to 1 over the function, so 1 over 3 minus 5x, times the derivative of what's inside the brackets, which is minus 5. So our result is minus 5 over 3 minus 5x. Always do it the same way, and always talk to yourself. An interesting yet basic example is when we have to find the derivative of y is equal to log 2x to the base e, for example. Just using our basic approach, we find that dy dx is equal to 1 over the 2x times the 2, which is equal to 1 over x. But the interesting thing is that the derivative of log x, not the 2x, just the x, is also 1 over x. So why do we get the same result? Think log laws. If we have log 2x to the base e, we can write that as log 2 to the base e plus log x to the base e, because the 2 and the x were multiplied together. And log 2 to the base e, of course, is a constant because you can get the value of that from your calculator. So when we differentiate a constant, that disappears, and leaving the derivative of log x to the base e, which of course is just 1 over x. So it's common sense that the two results would be the same. Next example. Find the derivative of y is equal to 4 log 3x squared plus x plus 2 to the base e. We do nothing different. Talk to yourself. So dy dx is the 4 out the front as just a decoration, put it down. The derivative of the log is 1 over 3x squared plus x plus 2 times the derivative of what's in the bracket, which is 6x plus 1. So tidy that up, we have 4 outside of 6x plus 1 all over 3x squared plus x plus 2. Now in the next example, we're going to find the derivative of y equals bracket 2 log x to the base e all cubed. Now remember the structure, everything is cubed here. So therefore you can use our chain rule in an ordinary way that we did before. So dy dx is equal to, bring the 3 down the front, rewrite the brackets, 2 log x to the base e, take 1 off the 3 to give us a new index of 2, then multiply by what's inside the original brackets. So the 2 just goes down because it's a constant, and the derivative of log x to the base e gives us 1 over x. So tidy that up, 3 times 2 is 6, bracket 2 log x to the base e all squared, all over x. For the next example, we have something that looks a little bit similar to the previous one, but there's a huge important difference in the structure. Here we have y is equal to 2 log x cubed to the base e. Notice that the 3 only applies to the x in this example, whereas the 3 applied to the whole term in the previous example. So we can really take the 3 as the index using our log laws down to the front. So therefore we've really got 2 times 3 of log x to the base e. Always think, can I use the log laws here? Very important. So now dy dx is a very simple procedure. 2 times 3 is 6, and log x to the base e is 1 over x, so therefore it's 6 over x. Important to remember the distinction. In the next example, we're going to find the derivative of y is equal to log 3x minus 2 over x plus 5 to the base e. Now you can recognise that from your log laws because we had log a over b, which was the difference between the two logs. So here our quotient is 3x minus 2 over x plus 5, so we can split that up into the difference between the logs. So it's log 3x minus 2 to the base e minus log x plus 5 to the base e. Now it's easy to get the derivative. So dy dx is equal to 1 over 3x minus 2 times the 3 minus 1 over x plus 5 times the 1, and then we bring that back together by bringing the two denominators together, and we get 17 over 3x minus 2 times x plus 5. Now for our last example, in terms of taking straight derivatives, we're going to find the derivative of y is equal to log x plus 1 to the base 10. Here we have a problem, because when we're doing calculus, the base always have to be a base of e, not a base of 10. So we have to get rid of the 10 and change the base so that it's an e. And we can do that, of course, using our change of base log law. So we simply split up the two components of our expression. So we have a log of x plus 1 over a log of 10, and then we get to choose the new base that we wish. Well, of course, if we're doing calculus, we have to have a base of e, so we put in an e in both of those. So we have log of x plus 1 to the base e divided by log of 10 to the base e. Now this becomes fairly straightforward because the log of 10 to the base e is just a number. It's just a decoration. So put it down where it is now, underneath. The derivative, I'll get it in a minute, of log of x plus 1 is simply 1 over x plus 1. So our resulting derivative function is 1 over log 10 to the base e times x plus 1. Of course, there's always a range of other sorts of questions which are based on you getting the correct derivative and then applying that into a special case. So in this particular example, we're going to have to prove that the tangent to the curve y is equal to log x to the base e at the point where x equals e passes through the origin. So first step is to find the gradient and the y value at x equals e so that we're going to be able to find the equation of the tangent. So dy dx is simply 1 over x, and at x equals e, the y value is log e to the base e, which is simply 1, and dy dx, the gradient, is going to be 1 over e. So the second step is to find the equation of the tangent using our normal structure for a straight line. Y minus y1 is equal to the gradient outside of x minus x1. So we have, in substituting, y minus 1 is equal to 1 over e outside of x minus e. We can expand our right hand side and we have x over e minus 1, and then tidy it up because the minus 1's are cancelling on both sides, leaving us with y is equal to x over e. As there is no constant term in this equation, the tangent must pass through the origin. Nice and straightforward, but a fairly typical question of the sorts of other things, tangents, normals, etc., that you're going to have to figure out. So keep your wits about you. So in summary of the main things to take out of this video, we can say the derivative of log x to the base e is 1 over x. We must always ensure we have a base of e when we're using calculus techniques with logarithms. And to get the rhythm of differentiating log functions, we want to say to ourselves, log differentiates to 1 divided by the bit after the log, and then the fraction that we've just created is multiplied by the derivative of that bit after the log. So good luck with your differentiation of logarithmic functions. Thanks for watching. Hope it clarified the approach for you. Go and do test yourself 1 on differentiating of logs. You will find it on my website at drjaysmaths.com. Hit the like button and subscribe if you haven't already. In the next video in this series, we look at integration of logarithmic functions.